7 stars show signs of activity from advanced extraterrestrial civilizations. This sensational news was published by scientists who used the James Webb Space Telescope to search for Dyson spheres in the universe. 7 stars showed such unusual infrared radiation that the probability of the existence of Dyson spheres there has increased dramatically. The strange darkening observed around the 7 stars cannot be explained by known natural phenomena. But have aliens really built gigantic power stations around stars, or is there another explanation? Scientists are certain 7 stars show such striking structures that they fit perfectly into the Dyson sphere scheme. Dyson spheres are hypothetical megastructures that advanced civilizations could build around their home star to harness all of the star's energy. This type of energy generation characterizes Class II species. The idea of such civilizations goes back to the Russian researcher Nikolai Karnashev. He divided potentially intelligent extraterrestrial races into 3 classes. The more advanced a species is, the more sophisticated its energy generation systems are. The physicist Freeman Dyson expanded Kardashev's theory and suggested that such power plants could completely or partially enclose the star and absorb its energy or radiate it as heat. This energy could then be used by a civilization to power its advanced technologies and needs. Dyson spheres have long been purely hypothetical assumptions, but in recent years, researchers have found more and more evidence that they really do exist. Some unexplained phenomena in the universe point specifically to the existence of such power plants. Around KIC 846-2852, also known as Tabby star, such a sphere was suspected until the eclipse was officially classified as a dust cloud. Some researchers even speculate that the gigantic voids in the universe are not real empty spaces, but have been deliberately shielded by extraterrestrial civilizations in order to divert the energy of entire galaxies for specific purposes. This would then be an indication of a Class III species that can theoretically use the entire universe as a power plant. Of course, researchers are now also using the advanced capabilities of the James Webb Space Telescope to unravel the mystery of Dyson spheres in the universe. They found 7 suspicious stars. Suspicious darkness in space. It sounds crazy to search the universe for dimmed or even invisible stars. Theoretically, Dyson spheres can cause both anomalies. They can eclipse a star periodically or completely. Theoretically, Type II civilizations could use their own star as a power plant, or Type III civilizations could also dim other stars in the universe to secure their energy. Scientists are therefore focusing their search on stars with inexplicable dimming phenomena and anomalies in the space-time structure that betray stars that are present but not visible. An international study has shown that a large number of stars have disappeared from the star catalogs in the last 100 years. Others have appeared as if from nowhere. Here too, the alien hunters set out in search of evidence for Dyson spheres. The phenomenon of stars disappearing completely from the scene is one of the hottest clues for Dyson spheres. Similarly, stars that are no longer used as power plants can suddenly reappear. To get to the bottom of Dyson spheres, scientists searched many other global data collections from the universe. Special attention was paid to technosignatures that differed significantly from natural signals and structures and thus indicated the activity of extraterrestrial civilizations. Strange radio signals, unusually regular darkening rhythms, or phenomena in the space-time structure for which there is no other explanation are the first indications of technosignatures. The scientists found what they were looking for, particularly in the extensive astronomical surveys of Gaia, 2MASS, and WISE. These satellites collected countless amounts of information on billions of stars over many years. To cope with the immense flood of data, the researchers developed special data pipelines and filters to identify stars that show signs of technosignatures. After the pipeline had filtered out the natural sources, a list of potential candidates remained. These were further investigated by looking at factors such as hydrogen alpha emissions, optical variability, and astrometry. Hydrogen alpha emissions are special light emissions that occur when electrons in hydrogen atoms fall from a higher energy state to a lower one. These emissions are typical for star-forming regions or active stars. The values help in the search for Dyson spheres if no significant hydrogen alpha emissions are found. This may indicate that the observed infrared radiation does not originate from natural stellar processes, but possibly from an artificial structure, such as a Dyson sphere. Optical variabilities are simply changes in the brightness of a star over time. Natural causes of optical variability can be pulsating stars, binary star systems, or rotations. A Dyson sphere would affect the brightness of a star in a way that produces different frequencies than natural events. If optical variability is completely absent or unusual patterns appear, this is evidence of an artificial megastructure used to generate energy. Researchers use astrometry to measure the positions and movements of stars. If movements and anomalies are detected that cannot be explained by known natural phenomena, this is also a strong indication of the existence of an artificial structure surrounding the star. Found 7 stars with Dyson spheres. Can you imagine that after analyzing about 5 million stars, only 7 potential candidates remained? The results sound sobering at first, and yet it is a sensation. 7 stars with a high probability of a potential Dyson sphere. That means 7 times the chance of finding extraterrestrial life. All 7 stars show clear excess radiation in the mid-infrared region that cannot be explained by known natural phenomena. And amazingly, all 7 are M-dwarf stars. M-dwarf stars are a class of stars that belong to the M spectral class. They are the coolest and smallest stars in the main sequence with surface temperatures between 2400 and 3700 Kelvin, and a brightness that is often only a fraction of that of the Sun. In terms of size, they also appear tiny at 0.08 to 0.6 and a diameter of around 20% to 70% of the Sun's diameter. However, these stars have an extremely long lifespan, often spanning several billion to trillion years. This makes them almost perfect for the emergence of life in their environment and for the further development of any civilizations living there. Due to their longevity and moderate radiant power, M stars could be the perfect long-term power plants. Now it's up to the James Webb Space Telescope to provide us with further data and evidence. James Webb Telescope, the perfect tool to find Dyson spheres. How will the James Webb Space Telescope now advance the search, and when can we expect the first evidence of the real existence of Dyson spheres? The spheres most likely emit a significant amount of infrared radiation as they absorb the energy of their star and radiate it as heat. The Webb telescope is designed to measure such infrared radiation. With its high sensitivity, it can scan the sky for the finest and most unusual infrared sources and collect data on their intensity and exact spectrum. Any conspicuous infrared signal that cannot be explained by known astrophysical processes could be an indication of a Dyson sphere. Through comprehensive spectral analysis, scientists are still getting more detailed information about these 7 stars and their surroundings. If a Dyson sphere is indeed present, the spectrum will show anomalies such as specific infrared excess radiation. Webb's MIRI instrument is capable of detecting large artificial light sources on exoplanets and would probably also be able to filter out artificially altered light from the natural light spectrum of a star due to Dyson spheres. The telescope has demonstrated the incredible wealth of data that can result from this by detecting several biosignatures in the vicinity of the exoplanet K218b. Webb finds biomarkers in the vicinity of the planet K218b. K218b is an exoplanet located about 124 light-years from Earth in the constellation Leo and has proven to be a promising target in the search for extraterrestrial life. K218b orbits the red dwarf star K218 and is clearly in the habitable zone of its star. This means that the planet could have liquid water on its surface, which is a prerequisite for the emergence of life. One of Webb's most remarkable discoveries was the real presence of hydrogen and water vapor in the planet's atmosphere. This is of great significance as water is the crucial element for life. The telescope's ability to analyze in detail the atmosphere of such a distant planet is an unprecedented scientific breakthrough. Webb has also identified 4 gases that are unique biomarkers in the atmosphere of K2-18b. Biomarkers are chemical compounds that are associated with biological processes and can therefore provide clues to the possibility of life. One of the most important biomarkers discovered is methane. On Earth, methane is mainly produced by biological activities, such as microbes and other living organisms. The discovery of methane in the atmosphere of K2-18b could therefore be a strong indication that biological processes could also take place there. Another important biomarker detected in the atmosphere of K2-18b is ammonia. Ammonia can also be produced by biological processes or by geochemical processes. Here, the simultaneous presence of hydrogen, water vapor, methane, and ammonia makes the difference, because all 4 together form the picture of a living world. K2-18b is a Hycean water planet, and this category of planet is statistically considered perfect for the formation of life. The possibility that K2-18b is a super-Earth, or in other words, a planet with a mass greater than that of Earth but smaller than that of Neptune, makes it particularly interesting. Super-Earths are common and could provide a variety of environments that could support life. An important aspect of the study of K2-18b is how the chemical composition of the atmosphere remains stable over time, and whether there are mechanisms that continuously replicate the observed biomarkers. Research is currently focusing on what the conditions on the surface of K2-18b might look like. Is there an ocean of liquid water there? Is there geological activity that contributes to the preservation of the biomarkers? In a second round of observations, Webb is to clarify further urgent questions. The first spectral analysis shows the scientists the way forward. Now they know that they must continue to search explicitly for traces of life in the vicinity of K2-18b. The observations of the JWST on K2-18b are the most detailed picture of an exoplanet that we have ever had. What this telescope can do is truly incredible, and looking at the feat that Webb has accomplished around K2-18b, we can be sure that Webb is also on the trail of the existence of Dyson spheres in space. Click subscribe now. The best videos are yet to come.